Hi and welcome back. Today we're going to try a different technology for giving classes. I'd like your feedback. Okay, so let's do a review of what we've done so far. So a review of what we've done so far is we've looked at the temporal difference, the idea of temporal differences, and we looked at this idea of the new average. We're going to check the new average. The new average is the old average plus this alpha k times the new data minus the old average. In some sense, this gives an error. This gives our error, our temporal difference error. Okay, and we're just going to update the old average with alpha k times the error. And notice if alpha k is 1 on k, it gives us the average. Okay, and then we did Q-learning, which stores an array of Q indexed by S and A, a two-dimensional array of students, of states and arrays combined. And then what happens when we get an experience, remember an experience was a tuple. If you're in state S, did action A, received reward R, and end up in state S prime. That's what happened to the agent. And this is going to provide new data for an estimate for Q of S of A. And this new data it received reward R and got the discount gamma, and then it got the new future value, which is the maximum over O prime of Q of S prime of A prime. Okay, so this is the value of S prime. Right, so this one here is the value of S prime. So it's the reward plus gamma times the value of S prime. Okay, and now we're going to put that into the temporal difference formula above. We're going to get Q of SA gets the value of the old one, which is Q of SA, plus alpha K of the new data, which is R plus gamma, the max over A prime of Q of S prime, A prime minus Q of S and A. Okay? And that is what we're going to use for our in Q-learning. Okay, so this is now new. We're going to update Q by this. So we're just averaging in all of the future estimates. So here's the algorithm. Here's Q-learning algorithm. So it's basically putting these things together. And this is a common structure in what we're going to do. So we're going to initialize Q of S of A, initialize Q of S and A arbitrarily. So it doesn't matter what we doesn't matter which way what we're going to start with. Doesn't matter for the correctness, but it might matter for the efficiency. Okay, we're going to observe the current state S. And then we're going to assume that the agent goes on forever, so it repeats forever. Sometimes people do it in episodes, which are finite sets of goals, but we're going to assume here it just goes on forever. We select and carry out an action A. We select and carry out action A. All right, so select and carry it out, and then we're going to observe R and this new state S prime. We will observe reward R and the new state S prime. Now we're going to update Q. So it's just a formula above. Q of S of A gets the value of Q of S and A plus alpha K times R plus gamma max over A prime of Q of S prime A prime minus Q of S and A. So the only thing we're using here is this Q. Often this often alpha K is fixed. Otherwise, you need to construct a count for every Q for every Q of S of A. There's an extra array to do the counts to do this. All right, so the interesting thing about this is it doesn't matter what action you carry out, this will still converge to the local optima. And as we saw last time, different ways of exploring, different ways of updating alpha k make a difference in how things work. Okay, and then there are a whole lot of exploration strategies we looked at. We looked at just the simplest epsilon greedy. We looked at ones where it's more likely to select good actions than bad actions. We looked at optimism in the face of uncertainty, and upper confidence bound, which take into account the average and the variance in order to choose the value that work is doing. All right. So there are a few problems with Q-learning. So problems with Q-learning. Problems with Q-learning, which we're going to adjust. The first one is it only does one backup between each experience. It only does one backup between each experience. That's right, one backup between each experience. So if you look at the algorithm above, when it selects an observation and observes reward, it only does one backup. It only learns about one Q. So it turns out it's possible to learn about lots of different Qs from observing this, and particularly could learn a lot about the past by using more information. So the alternatives to doing this, the alternatives to just doing one backup is what we can do is we can remember the previous experiences, and use these to update Q. To update the model. This is called action replay. And this is useful both for the case where actions are expensive, like a robot working in the world, actions are expensive, so we want to use the data as well as possible. And also in some cases because we'll notice that when we're in some particular region of the space, the samples are not random. So they're actually highly correlated, the samples, and so we actually get misled. Particularly neural network models get misled if we just do straight Q-learning, we have a function approximator. Is you need to do action replay in order to do avoid what's called catastrophic forgetting, which is the idea is that because it thinks the current experiences which are highly correlated are good ones, it actually forgets about the past. That's actually useful to do, except in the simplest cases. We could build a model. And use our Markov decision process techniques to solve it. And the other one we could do is we could do multi-step look-aheads, backups, or look-aheads. We could do multi-step backups, or we could do multi-head look-ahead. A common way to do it is to search. When we get an estimate of our current Q, we actually search forward because we know we can search forward through the Qs to actually make sure that we get a better estimate of the current estimate that we can now update. Okay, and the other problem is that it learns separately for each state. It learns separately for each state. And that's problematic, because we don't really want to work in terms of the state space. Most real-world problems are just too many states. So we want to avoid that.